There are two primary classes of photoreceptors, rods and cones, whose names describe differences in their morphology or shape. But there are other anatomical and functional differences as well. Whereas rods cover the entire visual field, except the fovea, cones are more densely packed in the fovea. Functionally, rods are highly sensitive to low illumination, that is, to low light levels, and are consequently most useful during night vision. Cones, by contrast, are sensitive to high illumination or bright light, and are therefore used for day vision. Another functional distinction is their role in colour vision. Whereas cones, which come in three types, are sensitive to colour variation in the image, rods are insensitive to colour variation. There are three classes of cone: short wavelength sensitive cones, middle wavelength sensitive cones, and long wavelength sensitive cones. Short wavelength light approximate our experience of the colour blue or violet. Middle wavelength light approximates our experience of the colour green, and long wavelength light approximates our experience of the colour red. There are approximately 6 million cones in each eye. In the case of rods, these are far more numerous. And as I said, rods aren't located in the fovea at all, whereas the cones are. This variation in the relative density of rods and cones across the visual field can be seen graphically in the figure on the left. The x-axis in this figure, labelled eccentricity, represents a single lateral cross-section through the left eyeball. Eccentricity refers to the distance from the point of fixation, that is, the eye's fovea. So, 0 eccentricity represents the fovea. Increasing eccentricity implies the image being projected further into the periphery. The numbers to the left of 0 eccentricity, labelled temporal, represent the half of the retina closest to the left ear. The numbers to the right of 0, labelled nasal, represent the half of the retina closest to the nose. The graph's y-axis describes photoreceptor density. Now, there are a few features of this graph I'd like you to notice. The first is the density of cones, indicated by the red curve, is sharply peaked in the fovea and falls off dramatically as one moves into the periphery. By contrast, the rods, represented by the blue curve, are absent in the fovea, but far more numerous than cones in the periphery. These differences have functional implications for how we see. The first of these is colour vision. Of course, the cones, which, as we've mentioned, are responsible for colour vision, are relatively underrepresented in the periphery. Our perception of colour is also relatively poor in our peripheral vision. Another functional implication involves night vision. Have you ever noticed, when looking at the night sky on a very dark night, that it's very difficult to see dim stars when you look directly at them? It's in fact easier to spot them if you look just to the side of the star. And this is because the receptors that are most sensitive to very dim light are the rods, and these are absent in the fovea. Another functional implication of these differences in cone and rod density is visual acuity, that is, visual resolution. The cones, which are functionally useful in daylight conditions, are underrepresented in the periphery, meaning we're less simply efficient at sampling peripheral vision than we are images on the fovea. Now, the final component of this figure that I'd like you to notice is the vertical white stripe, which is labelled here as being the optic disc. The optic disc is the region of the retina where there are no photoreceptors. The reason for this is that this is where the retinal's neural fibres are bundled together and leave the eye to connect with the rest of the brain. A curious consequence of this is that we actually have a blind spot in each eyeball.